Alright, this is Mr. McMurray, and we're going to talk about the Earth moving and try to make some waves, but they're going to be earthquake waves, it turns out. And we're on chapter 26, which is the chapter about, the architecture of the Earth. Basically, what does the inside of the Earth look like, and how do we know that? Alright, since no one has ever been inside the Earth, despite Journey to the Center of the Earth and a few other movies and books of the same sort. I hate to disappoint you, there are no wild dinosaurs and cave people living in the center of the earth and so forth. But anyhow, let's talk about what is there and how do we know about it. Alright, and basically, since we've never been there, most of what we know about the center of the earth comes from earthquakes and earthquake waves. Alright, and most of that comes benefit of a machine called a seismograph. Okay, which is used to measure those waves. Seismic waves, just another way of saying earthquake waves. Okay, anytime you see seismo, okay, it's going to have something to do with earthquakes. Seismic waves are going to be earthquake waves. Seismologist would be someone who studies that. Seismograph is a machine that measures those waves, and we'll talk about that here in a little bit. And basically, well, let's do that first. The problem is, if the whole Earth is moving, how do we make a machine that shows us how that's moving? Because if the whole thing moves together, then it doesn't really change much. And what we do is, we take a machine, we bolt it down, not to the surface, but deep enough into the ground that it's into the bedrock or solid rock. All right. Now that anchors it securely to the earth, but in an earthquake, the whole earth is shaking. So basically, everything on the earth is going to be shaking with it. So how are you going to measure that? Well, it turns out we put a mass, a very heavy weight here, and we put a pin underneath it. All right. The mass has inertia. So when the ground actually shakes down here, okay, when this shakes back and forth, unlike on my drawing here, this mass, its inertia means it wants to stay still. So what happens is, as this whole machine with the roll of paper down here moves back and forth, this part stays still. So down, for example, if the earth moves this direction, the pin stays still and marks there. When the earth goes back the other direction, then the pin's going to end up on this side and goes back and forth. It looks like it's going back and forth, but really it's staying still, and the earth is moving back and forth. And the marks that we see down here on the paper tell us how much it's moving, which gives us the strength of the earthquake wave, how strong is it, and things like that. When we get a rating on the scale of it, on the Richter scale, named after a man named Richter who invented it, the idea to measure how strong an earthquake something is. Okay, and so basically that's what happens. We anchor it to the earth, it moves with the earth, but the weight with the little pin on it does not. Since it stays in still and this paper below it moves back and forth, then that causes the pattern, which gives us the seismograph. Okay, and the seismograph tells us when the waves hit, okay, and how strong they were. Now, some of the rules about earthquake waves is, first of all, it depends what they're moving through. Waves move the fastest through solids, okay, and then followed by liquids, and finally, least of all, through gases and things like that would happen. Okay, so they would go very slowly in air. Okay, so there's not much purpose above the surface of the earth trying to measure these. We have to be down inside the earth, and so it moves through solids and also liquids. All right, but they move at different speeds through these, so we can tell based on how fast the waves are moving whether they're going through solids or whether they're going through liquids. All right, air pockets could also include things like caves and stuff like that that might affect that, but for the most part, when we're talking about middle of the earth, we're talking about mostly solids, but also liquids. All right. We can also tell between different types of rocks. The more dense a rock is, and the more elastic, or the more it will move out of shape but then move back to snap back to where it was before. Those are going to also have faster, the earthquake waves will travel faster through rocks that are very dense but very elastic, meaning they'll stretch but snap back into place. Okay, other rocks are usually less dense, all right, and they are more what we would call brittle. Okay, and they don't snap back very well, and the earthquake waves will go slower through them. So not only can we tell you if it's solid, liquid, or gas, but we can also tell you something about the rock layers, okay, and how dense and elastic they are, or if they're very brittle and therefore less elastic. All right, and so the change in speed tells us these different things about the inside of the Earth. So even though we've not been there directly and seen these things, we can, based on this data, tell us a little bit about it. All right, we'd like to know more, and there are places where they have tried to drill direct in the Earth. We may do a reading on that later. And basically, we've gone about 7.5 miles, 7.5 miles into the Earth's surface. But that's not very deep compared to how large the Earth is. But that's about as far as we've been able to drill so far. That's the world record. Now, there are some places that may have gone actually a little bit deeper because they've actually been in the ocean crust. And the ocean crust is shallower, and therefore they have been able to go deeper. Now, despite the fact that seismic waves move at different speeds, there's also different types of waves, okay? And so let's talk about some of the types of seismic waves. All right, the first type we're going to talk about are surface waves. Needless to say, these are waves that move along the surface of the ground, okay? So the surface waves move across the surface, all right? These are the slowest waves, all right? And they are they're the last ones to be recorded. Okay, when we have these seismograph stations where they track these things, these are some of the last waves to get there. Okay, so to be honest, if we can measure some of these other waves that travel below the surface, we would technically know that the surface wave was coming a little bit before it got there. Unfortunately, we're still talking about fairly fast speeds. There's not that much of a lag time, and certainly not enough to evacuate a city or large areas or anything like that. So it's not the most helpful thing in the world in that sense, but they are the slowest ones. So we have a little bit of warning before the other waves do. But these surface waves are the ones, since they're at the surface where we live, they are the one that cause the most damage. All right, and so most of the damage that's done is done by these surface waves. All right, and there are two types of surface waves. One is a Rayleigh wave, or Raleigh wave. To be honest, not sure which way to pronounce that, but it looks to me like Rayleigh. Okay, Rayleigh wave, so that's how I usually pronounce it. It's compressional, which means that it is scrunching together, then spreading apart, and then scrunching together, and then spreading apart. Kind of like sound waves, if you were here for the last semester where we did some of the physics, but they squish together like a slinky. If you grabbed a slinky together and let it go, it would scrunch together, spread apart, scrunch together, spread apart, scrunch together, spread apart. Okay, obviously, just something on the surface, that's going to cause a lot of problems. Now, the other bad news is they are also transverse, meaning they go up and they go down like a light wave does. Okay, and so you've got stuff being scrunched together and going up and down, rippling like this. Obviously, this is not good for things on the surface, which aren't really built. Most things aren't built to allow for that kind of motion, and so it does a lot of damage to the surface. Love waves, on the other hand, are transverse, but they go from side to side like this. And so as you can see, the fence, if you had a straight fence or a railroad or something like that running, after this one, it might go wavy from side to side. Okay, whereas a Rayleigh would go up and down and would pitch things up and down like that. Okay? And I'm making all these hand motions that you can't see, but maybe when we have the lecture I can explain that. All right. The second type after these are, there's the surface wave. They cause the damage and everything. That's what caused the earthquake that we feel. But the ones that are probably more important to us as far as knowing what's happening inside the earth are body waves. Body waves travel inside the Earth, okay, through the interior. All right, so they travel through the interior of the Earth. All right, and as they go through the interior, they change speeds, and this is what tells us a lot about the inside of the Earth. All right, so for body waves, we have two kinds. The first, which are the fastest, so therefore the first ones to get there, okay, are called primary waves. Okay, primary because they are the fastest, and so they're the first waves to reach our recording stations. All right, and so they are called primary waves. Now they are like sound waves; they are compressional. Okay, which means that they are pushing together, spreading apart. And you can see on the lines here, they're spreading closer together, farther apart, closer together, farther apart. So as this is doing kind of like a giant slinky or an accordion on the ground, you can imagine this is doing a lot of damage to things. But they're compressional, and they are the very fastest ones. The other important thing is that they can travel through, they go through solids, and they also go through liquids. So they go through solids and liquids, which we'll see in a minute, not all waves can. So it can go through both of those. And they're also called P waves for short. So just if you see P wave, that's all we're talking about, P waves. Now the others are secondary waves. All right, secondary waves, or otherwise known as S waves. Secondary shows they're the second waves to get there. Okay, so they're a little slower, so they're slower than the others. The P waves get there first, then the S waves would show up next. All right, now they are transverse waves. Transverse waves, and they also then go up and, whoops, I am not going with the thing there, but you get the idea. They're going up and down, so primarily. All right, whipping up and down as they travel through the Earth. They're going up and down. All right, and they are different in what they can travel through in that they can only travel through solids. They travel through solids, but if they hit liquid, all right, they cannot go through a liquid, and they will just stop. All right, and this is very important because there's parts of the Earth, the center's core, that we think are liquid, and we think that because these waves stop when they reach those. All right. Now, so how do we use the different type of seismic waves to tell us more about the Earth's interior? Well, on the Earth, we have different stations, and these little stations are set up at all different places across the globe, you know, scattered at different places. Ironically, many of these seismograph stations were put in place originally to pick up the vibrations from Soviet or American nuclear explosions back in the 40s and 50s. First part of the arms race, they didn't have all the satellites and stuff going around the Earth, so the only way they could know is that they picked up those vibrations. So they built an extensive system in the United States and in Russia and other countries so that they could pick up those vibrations. And ironically, a lot of those are now used for earthquakes. But anyhow, as it goes through these different layers, as these waves, we said, go through the center, they go and they hit different layers. And as they go through, they send reflexive waves back to the surface, okay? And by measuring those waves and how fast they're moving, this tells us a lot about it. Now, besides that, besides the reflections coming off, also when a wave is coming through here, if it hits a curved surface, this is kind of like a lens, okay, like a lens in our glasses. And just like light rays are bent, okay, if it's coming in and say the top part of it hits this first, if it slows down, then it would tilt this direction. And so this wave that was coming like this now is going to tilt and go off a different direction. If it were to go faster when it hit this part, when it came in here, now it's going to tilt and it's going to go this direction, okay? So based on whether they speed up or slow down, therefore turn right or left, basically, that tells us a lot about the surface. It's curved, and also if it's made of a different substance, like a solid versus a liquid. All right, and we will pick back up on this in just a second.